Okay, so it's 3:10. Welcome to the session on type theory. And the first talk is a distinguished paper award by Andrei, Popescu, and Dmitriy Traytel on admissible types to PERS relativization on higher order logic. And it will be given by two people, so it should be entertaining enough that everybody's awake after sort of a long day.
Right. Thank you very much, Brigitte, and thank you for attending our talk. And also many thanks for the award. We'll try not to disappoint with the presentation. So I'm going to give a talk together with my friend Dmitry on admissible types to set relativization in higher order logic. The context of our contribution is the area of proof assistance. Proof assistants are well known at POPL. There's a large number of such wonderful tools and increasing such wonderful tools. Most of the mainstream proof assistants are based on higher order logic or dependent type theory. Higher order logic, I will abbreviate it as HOL, of course with some notable exceptions. And our contribution is in the area of higher order logic. So our contribution is relevant for proof assistants such as Isabelle HOL, HOL-4, and HOL Light that are based on higher order logic, and also partially relevant for extensions such as HOL Omega and for variations of higher order logic such as PVS. And we have a practical motivation for this work, and let me give a bit of the wider context. We in the theorem proving community, we like to talk about these great achievements in verification. SEL4 verified, the ComCert compiler, a proof of the four-color theorem, and so on. And it is right to emphasize these achievements because they are really inspiring for us and possibly inspire the generosity of funders of research in the area. But I would claim that these achievements are only the tip of the iceberg. The iceberg itself consists of proof assistant infrastructure. So we're talking about automated proof methods, powerful abstraction mechanisms, smart user interfaces that make such developments, such great achievements feasible. And what I would like to emphasize in this talk is the development of formal libraries, typically mathematical libraries of other kind, that represent the work of countless enthusiasts within the corresponding sub-communities of different proof assistants. And our contribution will be in this area, so we're going to make developments in higher order logic more productive. So this is where our particular technical contribution goes. So I would like to illustrate our contribution in terms of a fable involving two little pigs that are going to use different types of HOL material, lighter or heavier HOL material to build their formal development. They're going to be played by Dmitry and I.
Yes. So I built my house, and by that I mean my group library, using type-based formulation, because I love types. And here is how I define groups. I have a predicate that inputs the group operation and the neutral element, and I have the predicate is defined as the usual group axioms. And thereby, I use the fact that I represent the carrier set of the group as the type alpha.
Okay, so I'm older and slower. So the way I go for the same formalization, in addition to the type that represents the carrier of the group for Dmitry, I also consider a set, an explicit subset of the type, and define the same notion of a group by considering that set as a carrier. So basically, everything is relativized to that set.
Well, good for you, but I'm extremely productive with my formalization, and I proved this deep, famous, and fictitious theorem in group theory in only 10,000 lines of Isabelle, and it took me 2 months.
Oh, you proved the Abel-Galois-Klein-Lie-Ruffini theorem. That's impressive. I'll start working on this too. Yeah.
Yeah, and actually, while you are working on it, I even already applied the theorem. So I have a different application where I work with symmetric groups, and I could instantiate the theorem to get some nice properties of symmetric groups here. So what did I have to do to reuse the theorem in my setting? Well, I had to define a new type of permutations because I'm working type-based, and permutations are just bijective functions. And I have a huge library in Isabelle of theorems about bijective functions, but I could not reuse the library immediately. I needed to lift them to the new type. So that was a slight disadvantage.
Okay, so I'm also moving slowly. I'm making my way. I managed to prove the theorem, and it took me much. My formalization is quite a lot bigger because I have to carry these assumptions. So I have this invariance about the carrier set, and everything is done making these assumptions. But now let me see if I can instantiate the theorem. It's actually much easier for me than for you to instantiate the theorem because I have this set, so I don't need to define any type and do any transfer. So the instantiation of the theorem goes out of the box, obviously verifying the assumptions and the conditions of the theorem.
Well, it was still only 20,000 lines for me, and it took you.
Yes, it is true, but you're going to have to do this over and over again whenever you want to instantiate to an incomplete type, to a subset of a type. So it will eventually pay off. In a few years, I will catch up with you.
You might be onto something. So I do agree that we would like kind of to have the best of the both worlds. The type-based world, where we have very nice proofs within the library, and the set-based world, where we have very easy ways to instantiate the result.
Okay, so this is where our contribution will be. So what we are providing is a logically safe mechanism for essentially developing a whole library in the style of Little Pig 1, and for instantiating it flexibly in a set based in the style of Little Pig 2. But in order to delve into the contribution, first I need to do a really quick primer on higher order logic. Again, we abbreviate it as HOL. So this is, in a nutshell, this is rank 1 polymorphic simplified lambda calculus that is organized into a logic involving Hilbert choice and infinity. It is consequently a classical logic. The entire whole logic can be described on one slide. So we have the simple types, including bool and the type of individuals and the function types. We have terms, simply typed terms, and they include the equality and the Hilbert choice operator. We have definitions. So the logic can be extended with introducing new constants. For a fresh constant name, we just assign a term. There's no recursion involved. And introducing new types. Assuming that we have a non-empty predicate on an existing type, we can introduce a new type in a style that is essentially set theoretic comprehension. So we define a copy of that predicate as a new type, and we have some bijections with that particular predicate on the old type. For this reason, because this is so central in developing HOL, HOL is sometimes referred to as a type set theory. There are no connectives and quantifiers to start with, but they are definable from the existing operators, notably from lambda abstraction and equality. And we have a few axioms, just a few axioms. The equality axioms, the first was shown there, and then an infinity axiom stating that the type of individuals is infinite, and the choice axiom regulating the expected behavior of the Hilbert choice operator, namely that it actually chooses an element satisfying the predicate if there exists such an element. And we have deduction, which goes as expected. There are the expected introduction rules for implication. There's the extensionality axiom. Deduction is parameterized by a fixed definitional theory consisting of the currently introduced concepts and types, and by an evolving context as usual. So there's nothing special in the deduction. Okay, so this was HOL in theory. HOL in practice actually looks quite different. It's essentially a functional programming language endowed with possibilities to prove things about the programs. And this is because everything, induction, inductive data types, recursive functions, they are bootstrapped from this minimalistic kernel. And all these high-level mechanisms, the usual goodies for the functional programmer, are bootstrapped from the minimalistic kernel. So the user doesn't have to know where this all started, doesn't have to know about the beginning of the world, but the advantage is that having it done like this will create fewer opportunities for inconsistency bugs to sneak in. Okay, so now back to our problem. We have this simpler type-based definition statements and definitions. So in this case, a formula phi that expresses, in this case, a fairly trivial property of a group. So we have that for all groups, the operation is left cancellative. The exact property doesn't matter, but this is how you would formulate it in HOL. And then we have the relativized version, the set relativized version. We're going to write phi RLT for it, which introduces this carrier set explicitly. So quantifies explicitly about over a carrier set A. I'm using indexes to indicate the types. So this is a subset of the type alpha, namely an element of alpha set. And notice that we carry this everywhere with us. So in this particular example, we have really a fundamentally first-order relativization situation, so it's clear how this should look like. And our goal is to formally infer the relativization, the relativized counterpart from the original. Now, an additional question that we ask is whether this is doable in the without adding any new axioms to HOL. And the reason why we care about this is, of course, the fact that it's quite easy to introduce a new axiom for any new cool feature that you would like to add to a logic, but this decreases the trust. There can be problems with the design of the axiom, there can be problems with the implementation, and so on. So we would like, if possible, to do this without extending the axiomatic base. But a more basic problem that we want to address is the very definition of relativization, which turns out to be quite interesting in cases that go beyond the first order case. So really the question is, what structure and properties do we need in order for relativization to go through in general in higher order logic? So let's consider a few examples. We are, in a sense, on unexplored territory. We have the first order relativization, and now we want to extend it to higher order logic, but we need to have some guidelines, some desirable properties, and we're going to collect such desirable properties by analyzing some examples. Here is a second order example where there's some non-trivial interaction with equality. So there's this property that says that if you define an inverse operator on a group, this inverse is going to be unique. Okay, so any inverse function is going to be, any two inverse functions on the group are going to be the same. The way to relativize this is, of course, we carry this explicit carrier set A that is assumed to be closed under the operations. We use the relativized notion of a group. And we talk about two functions that preserve A, such that A is closed under those functions, and we want them to be equal, but we don't want strict equality, but we want equality restricted to A. So what we want is a set-based counterpart of the type constructor. So here's some structure that emerges here. And we also want to relax the equality relation. Type theory people are quite familiar with this notion of dealing with many equality relations. We are not so familiar with this in HOL. So we want to relax the equality relation to an equivalence relation in this case. in order to deal with function equality. Otherwise, the property would be too strong. Okay, so we have these ingredients, relaxed equalities and restricted domains, which means essentially partial equivalence relations. This is the closest concept that generalizes both of them. So pair is going to be the abbreviation that we'll use for partial equivalence relations. Okay, so we generalize the situation from types to sets to types to pairs. So what I show here is a slightly modified statement that deals with relations. So now these operators are dealing, like the function space lifting, are dealing with lifting relations. Everything has to be in the domain of the relations. And yeah, so the whole relativization essentially has the same shape, but now we work with partial equivalence relations. And what's important is that this extension is conservative over the set-based extension. So if we instantiate the relation to equality, then we get to equality over a set, then we get the set-based relativization. Okay, so we have concluded that we want something more general than sets. We want pairs. Now let's see another example. This involves a bit of functional programming on a group. So we have this fold operator. So we have this property that says that folding the concatenation of two lists, folding multiplication of the concatenation of two lists is the same as folding separately and multiplying the result. So this follows easily from associativity. How do we want to relativize this? This is a first approximation, so we essentially apply the recipe from the previous slide. And we have the relativized version of the different constants. We assume that we are in the domain of the relations. We assume that the operators respect the relations and so on. And one thing that pops up here is that obviously we want to have ways to lift partial equivalence relations along all the type constructors, not only the function space, so including all the defined type constructors. So lists, like all the data types and all the container types, they are bootstrapped in HOL in a set theoretic low-level fashion, so to speak. So we want to employ the relational interpretation of the container types. Now, in order to aim for a practically usable relativization, we also note another piece of optimization, namely, if an operator is already parametric, then it should not be affected by optimization. This is very intuitive, and roughly speaking, the intuition for this is that parallel relativization is the process of turning a term into a term that is as close as possible to it, while being pair parametric, that is parametric with respect to partial equivalence relations. And therefore, if it's already parametric, then there's nothing happens. Okay, so with these examples and others, we have gathered a list of desirable properties for relativization. We could call them, let's say, sanity properties. First, and this is very important, the high-level view of container types should coincide with the low-level view of such types as defined in HOL in a set theoretic fashion. Then we should obviously generalize full relativization. So we should be compatible with full relativization. And then there should be a certain tight relationship between the relativization of a term and the original term. So as I mentioned, it should be a pair parametric term that is in some sense close to that term. And here are some properties that represent that. And relativization should preserve probability. This is the provability. This is the problem that we started with. So we would like this to be an admissible rule in HOL. As a side note, it is actually not a derived rule in HOL. So this is something that I should have mentioned. One of the things that makes this problems interesting is the fact that it is not possible to derive even first-order versions of the relativization to derive them in HOL. But admissibility is an achievable goal. Okay, so with this list of desiderata, we are ready to describe the end product. We have the relational interpretation that takes a type into a term that expresses a relation, and the relativization. So these two operators go in pair. Essentially, the relational interpretation offers a translation of the type of the relativized term. And the interesting cases are shown in blue here. So the definitions go recursively on the structure of the syntax. For the relational interpretation, notice that nothing interesting happens for variables, applications, and lambda abstractions, in spite of the fact that we do want relativization of the quantifiers. And this is because we handle equality. This is because we take care of equality here. So equality on a type is relativized in the relational interpretation of that type. So it's a mutually recursive definition. Hilbert choice is of course, a notoriously non-parametric entity here. And there's some massaging that is needed here in order to achieve that we extend the original operator, and at the same time we achieve pair parametricity. So Hilbert choice is hopelessly non-parametric, even with a modification. But it was interesting to notice that if we restrict to partial equivalence relations, actually there are bits and pieces of parametricity that can be recovered by this translation. Now, the relational interpretation works as expected for the built-in type constructors. And for the defined types, we need to make a choice of a relation that is in bijection with the restriction of the relational interpretation of the original type relativized to the defining predicate of the type. And this is, it turns out that this choice doesn't matter for most of the properties that we care about, except for the compatibility with the container types. So we want compatibility with the natural recursively or co-recursively defined relators on the data types and codata types. And this is why we need some flexibility here in the choice. But this can be made to work. Now, a restriction is the fact that we want, this was an interesting cardinality restriction that popped up in this discussion about parametricity. We want the defining term to be sufficiently large, essentially relative to its relativization. More precisely, relative to the quotienting of its relativization to the relational interpretation of its type. So we call this wideness. Okay. So with this definition, we are actually able, and with the restriction to wide types, we are able to obtain these desiderata. So we're able to prove that relativization together with relational interpretation satisfies these desiderata that qualify our relativization for a, let's say, sane extension of first order relativization. And the corollary is that types to sets, which types to pairs conservatively extends, is also admissible. So this is the problem that we have started with. Now, what remains is this wideness assumption. So what are the consequences of this wideness assumption? And as well as a practical realization of relativization. I'm afraid I have cannibalized Dmitriy's time, but please go ahead.
Yeah, I have minus 1 minute to conclude, but I will conclude quickly. So all types in HOL are wide. That's what we checked. I will go quickly through that. Data types and codata types and all the type definitions that are involved in them are wide. And there are a few non-codata types that are also there in the whole distribution, and we checked them as well. For that, we used an implementation that implements our relativization infrastructure. This is the example from before, where we can relativize terms and relativize theorems. And when we are relativizing theorems, this is a prototype implementation. So currently, we just throw in the relativized theorem as an axiom. And then we can prove types as wide. Here, this is an example for the type of polynomials that happens to be in Isabelle's library. We prove that it's wide, and after the user finishes the proof, our infrastructure can relativize statements that involve polynomials. We did this for many types. There is some related work. I would say we are deeply inspired by relational interpretation and parametricity, but I think the special aspect of our work is that we work with partial equivalence relations. And they play a role in some dependently typed theories as well, so there are relations there. So our motto is to prove easily and still be flexible, and this is possible in Isabelle HOL because all types that are involved are wide. There are artificial counterexamples, but they are not in the whole distribution. That's it. Thanks.
Maybe we can take one or two quick questions. So we, was there? Yes, go ahead, Max.
Max New, University of Michigan. So your original motivation was to support theorems using subsets of types, but PERS should also give you quotients of types as well, right? So do you have applications of that that were useful?
There are quotient types in Isabelle, and they are implemented via subsets. So, yes.
Thank you.
Okay, maybe one last question here in the front. Maybe you can also state your name and where you're from.
Hi, I'm Jed Galliini from the University of Cambridge. So from what I understand, the implementation just inserts an axiom of the relativized theory. Is there a way to generate a proof, or did I just misunderstand that bit?
Yeah, very good question. I didn't have time to mention that. So our theory says that it is possible to generate a proof. There are technical problems in Isabelle. In particular, Isabelle does not record proof objects. There is a way to enable that, but that makes everything slow. But if we had proof objects, we could have a foundational tool that not only axiomatizes the theorem but proves the theorem. So we are looking into that.
All right. Well, thank you, and maybe.